We're going to look more specifically at a couple kinds of force. The first being gravitational force. Gravitational force is quantified by Newton's law of universal gravitation, which says that, and we'll often use F sub g for gravitational force, that's g subscript, is equal to capital G times mass 1 times mass 2 over r squared. Gravity is always an attractive force, so it pulls objects toward each other, and it does so proportionally to the mass, the product of the masses of the two objects, and inversely proportionally to the distance between the centers of the objects. G is called the universal gravitation constant, and it is 6.673 times 10 to the 11th, and then, as with many constants, the units are really goofy. It's meters cubed times seconds squared per kilogram. Anyway, we'll deal more with this a little bit later in the year when we talk about gravitation in the context of planetary orbits. For most of what we're doing, we'll be assuming we're on the surface of the Earth. And if we plug in g times the mass of the Earth times the radius of Earth squared, and whatever this other mass is, the mass of another object, this g times mass of Earth over radius of Earth squared comes out to 9.8. And so our gravitational force that we'll be using close to the surface of the Earth is just mg, or often minus mg if we're calling the downward direction negative. So gravitational force will be just mg. So the gravitational force is proportional to mass. Now when we're doing kinematics, we just said that an object is accelerated downward at 9.8. Well, why was that? If this is our force, if the only force acting is gravity, then using Newton's second law, we get mg equals ma, and therefore the masses would cancel out and our acceleration would just be the acceleration due to gravity, which is why when we were doing kinematics, we didn't care about what the mass of the object was, because objects of all different mass are accelerated to Earth at the same rate. Okay. I also want to look at what is called normal force. This isn't a fundamental force like gravity is, but it is a special enough kind of force to give it its own name. A normal force always acts when two objects are in contact. And it always acts perpendicular to the surface in question. Okay. Now you may not have thought about this, but let's, consider this calculator. It's on this desk. Gravity is acting on this calculator, and gravity is exerting a force on it that's going straight down. Now, why doesn't it go downward? Because the table is here, right? And this tends to give people a hard time if they think about it too much, because you guys, it's common to think of inanimate objects as, well, inactive, like they're not doing anything, right? The table's just sitting here, the desk is just sitting here. But this surface is applying an upward force that cancels out the gravitational force on this calculator. You know that because the calculator is not accelerating downward. If it's at rest, the net force must be 0. So the tables and desks and whatnot do exert upward forces on objects. If I push down on the calculator, which you may not be able to see me doing, but if I push down on the calculator, now there's more downward force on the calculator than just gravity. There's force from gravity and from my hand. Now there's a greater normal force that the desk is exerting. So normal force will tend to cancel out other forces if it will up to a certain point. Like if I push hard enough, I don't think I can push hard enough, but if we were to keep applying a stronger and stronger force to the desk, eventually it would break and we wouldn't have any more normal force. Well, there still would be normal force, but eventually it would break and then it wouldn't be keeping objects in place like it does. So the normal force, as I said, it acts perpendicular to the surface and tends to cancel out other forces. Okay. If I lean against a wall, then the wall is applying a horizontal force to my body. That is a normal force. And that horizontal force is keeping me from falling through the wall. So normal force, keeps you from going through objects. And like I said, it always acts perpendicular to the surface of an object. So if I have an object resting on a desk, and as we do the problems, we're going to be drawing a lot of diagrams. So I recommend anytime we do a force problem, draw it, and then draw vectors, arrows, representing all the forces acting on the object. So we've got an object on a flat surface, we've got gravitational force going down, and we've got normal force going up, which I write as F sub n. And this would be F sub g, which is mg. And so for an object resting on the table, we know our net force is 0 because the object isn't moving, it's not accelerating. The object is just totally at rest, it's not accelerating. An object could be moving and still not be accelerating if it's moving at a constant speed, in which case the net force would also be 0. But if an object is totally at rest, then there is no net force. And so that means that normal force minus mg is equal to 0. So in this case, the normal force would be equal to the gravitational force acting on the object. Okay. Now this relationship between normal force and gravitational force results in an interesting phenomenon called apparent weight. Now, most of you, I think, have probably ridden an elevator, and you might notice that when you're in the elevator and the elevator starts going down, when the elevator is accelerating downward, you kind of feel weightless or lighter for a second. And that's related to this phenomenon of apparent weight. So when the elevator is accelerating downward, the forces acting on you are the gravitational force and the normal force from the elevator, from the floor of the elevator. When you're accelerating downward, then you can say that the normal force minus the gravitational force is equal to, well, mass times acceleration. In this case, the acceleration being negative means that, your ma is a negative number, meaning that your normal force is less than mg. And the weight that we feel is actually the normal force. This is also the weight that will be read if we put a little scale. This is the scale. The scale actually measures the normal force that it's exerting. So if you're just standing there, as this is just sitting here, then that's equal to your weight, and so a scale will give an accurate reading of your weight. If you're in an accelerating elevator, then the scale, in this case, if you're accelerating downward, the normal force will be less than your weight, so then you will have an apparent decrease in your weight. If the elevator is accelerating upward, then that means that our normal force is greater than mg, and you have an apparent increase in your weight. Okay, and this is you've felt this too. When the elevator starts accelerating upward, you feel pressed down to the floor, or both when it's starting to go upward and when it's coming downward and it slows down. Right? And then if the elevator is going at constant speed, then your apparent weight actually is the same as your actual weight. I should make a comment that weight is the gravitational force acting on you. That's the definition of what weight is how much force the gravity of the Earth is exerting on your body. So your weight will change if you go to different planets. If you go to the moon has less mass than the Earth, so it exerts less force on you, and so you will have less weight. That's why the astronauts can, bounce around like they do, and objects fall more slowly and whatnot. but your weight will change as you go to different places, but your mass will not.